Hi there. I'm standing here outside of my lab on the 5th floor of Chamberlain Hall to tell you a little bit about AMO research here in the physics department at the University of Wisconsin-Madison. As you can see from the sign behind me, the one thing that really connects all AMO research is that we use a lot of lasers. There are 5 AMO faculty in our department: Jim Lawler, Mark Safman, Thad Walker, Denise Yavuz, and myself. As I think you'll see, there's a wide variety of exciting AMO research taking place in our department, but there are also a lot of connections between the different research thrusts, and there's a lot of collaboration between the different AMO groups and between the AMO groups and other physicists in our department and scientists all across campus. Now, let me try to convince you why you should get a PhD in AMO physics. For starters, it's an exciting field with many new discoveries. That's true for a lot of different fields in physics. But one of the things that makes AMO special is that it's a relatively small community. It's less than 10% of APS membership. Yet 5 of the last 20 Physics Nobel Prizes have been in AMO. One of the great things about AMO is that because the systems we work on are so well isolated and so clean, you can work on experiment, but you can also work on theory, and you can do a little bit of both. And if you end up doing a PhD in AMO physics, you almost certainly will work on both. Another nice feature of AMO physics is the scale of the experiments in terms of the time scales, the person scales, and the monetary scales. AMO experiments tend to be relatively small, just a few grad students, maybe a postdoc and a faculty member. And they tend to be experiments on the time scale of years, and they're tabletop experiments. You build the experiment yourself, and you get to see it through from start to finish. Another great thing about AMO, and one of the things that first drew me to the field, is that quantum mechanics is really your sandbox. You get to play around with isolated quantum systems that actually behave according to the laws of quantum mechanics. And if you're like me, and quantum mechanics has always kind of mystified and astounded you, it's really fun to get to play around with these systems in the lab and actually see quantum effects with your own eyes. Last and definitely not least, there are lots of career path opportunities for someone with a PhD in AMO physics. You, of course, can stay in academia. You can also go do research at a government lab, or you could end up doing industrial R&D. And there's a lot of startups and also major tech companies that are currently investing in AMO technologies, in large part because of the increased investment and excitement regarding quantum technologies. UW-Madison has recently joined 2 large-scale national quantum centers, and there's a lot of quantum growth in Madison and also around the country that UW-Madison Physics Department, the Wisconsin Quantum Institute, and our AMO faculty are really right at the heart of. Now that I've convinced you to go into AMO research for your PhD, let me try to convince you to do it here at the University of Wisconsin. So I'd like to tell you a little bit about the different research going on, and I think it'll give you a sense of just how diverse and exciting this field really is. First up is Professor Jim Lawler. Jim is a specialist in atomic spectroscopy and precision atomic spectroscopy and the development of new kinds of spectrometers. Jim's research is focused on both developing new kinds of spectrometers that will go up into satellites in order to study climate change and monitor greenhouse gas emissions, as well as precision atomic spectroscopy in order to better understand astrophysical data collected by telescopes and large sky surveys, so that we can better understand the processes that produce all of the heavier elements in the universe and on Earth, which are still really not well understood. Next up is Professor Mark Safman's lab. Mark specializes in quantum computing research with neutral atoms. He has a number of different projects and collaborations, but the central thread connecting all of his research is the use of Rydberg interactions between atoms in highly excited Rydberg states in order to create exotic entangled quantum states and to form the building blocks of quantum computers and quantum networks. As you can see from this slide, Mark collaborates with many of the other AMO faculty in the department and scientists across campus to work towards developing these quantum technologies. On this second slide, you can see one example of one of Mark's experiments where they have developed the capability to load roughly 100 cesium atoms into a 2D array where they can individually address and control each of those atoms, and each single atom forms a qubit that can be used to perform quantum computations. In Thad Walker's group, they're making quantum sensors out of atoms, such as ultrasensitive magnetometers. For example, here on this slide, you can see the atom-based magnetometer they made that is capable of detecting the incredibly weak magnetic fields generated by fetal heartbeats externally in an entirely passive and safe way. This information can then be used by doctors to detect certain health issues in the fetus and correct them in utero. On this next slide, we can see that the same atomic magnetometry techniques that are used by the Walker Group for medicine can also be used to search for new physics beyond the standard model, such as exotic forces and new particles. In Denise Yavuz's lab, they are studying the interactions between light and matter and are using exotic effects to gain new levels of control over the states and behavior of light. For example, on this slide you can see a crystal doped with the rare earth element europium that is fluorescing when excited by a laser. The europium in these crystals has unusual optical magnetic dipole transitions, which Denise and his students will take advantage of to engineer a negative index of refraction at optical frequencies. These materials might one day be used to make diffractionless superlenses or invisibility cloaks. And last, but hopefully not least, there is my research group. Our research is focused on precision measurement, nanoscale metrology, and quantum sensing. We are building a brand new kind of optical atomic clock capable of performing new tests of relativity and searching for certain kinds of dark matter. We are also developing new quantum sensing techniques with atom-scale defects in diamond, and are applying these techniques to study the origins of decoherence in the materials and devices used for quantum computing, quantum sensing, and to build quantum networks. And finally, since you unfortunately can't be here in person to visit our labs, let's do a quick virtual tour of an AMO lab. Here we are inside of my lab. What you see on that big heavy optics table is called an optical lattice atomic clock. Inside of this stainless steel vacuum chamber, we have pumped out all of the air, so the inside is actually very similar to deep space. Next, we use lasers to cool thousands of strontium atoms down to a temperature of just 1/1,000,000th of a degree Kelvin above absolute zero. So when the experiment is actually running, the inside of this vacuum chamber is one of the coldest places in all of the universe. Finally, we trap and hold these atoms inside of an optical lattice, a kind of crystal made out of laser light. The reason we do all of this is to make a special kind of atomic clock that is so precise, if you synchronize two of these clocks at the Big Bang and left them ticking side by side for the entire 14 billion year age of the universe, they would still agree with each other on the time today to better than 1 second. Over here on this other table, you can see that in order to make this experiment work, we use many different lasers. That blue light you can see is just one of the 7 different lasers we use for this experiment. All of the different components you can see here on the table are optics we have very precisely aligned in order to control the frequency, intensity, and shape of the laser light, before we use optical fibers like this to transfer that light over to the other table with the experiment, where we use the light to cool, trap, control, and interrogate the atoms that we have inside of that vacuum chamber in order to make our clock. Of course, putting together a complex AMO experiment like this and using it to do exciting science is a lot of fun, but it's also a lot of work. Most of the experiments I've told you about in this video have openings for new graduate students. And if you decide to join us here at UW-Madison, you can help build a next-generation ultra-precise atomic clock capable of measuring and testing general relativity in the lab, or build the world's most powerful quantum computer. If you're interested or have any questions, please come chat with me or any of the other AMO faculty during the virtual faculty meetings. So welcome to Madison, and we hope to see you here in person soon.